When we try to predict the real world, whether it's the stock market or a simple traffic jam, our usual tools can really fall flat. They're built for this kind of perfect, clean world, but reality? Reality's messy. So what do you do when you need a smarter, more adaptive tool to make sense of all that chaos? Well, you build a hybrid hero.
All right, let's get into it. First, we're going to look at why our classic tools kind of struggle. Then, we'll meet the two big ideas we're going to mash together. After that, I'll introduce you to our hybrid solution, the APKF, see it in action in a traffic jam, and then wrap up with why this whole thing is such a big deal for the future of smart systems. So, to really understand why our solution is so cool, we first have to get the problem. And that problem starts with a tool that's brilliant, but, well, it's got its limits. I'm talking about the classic Kalman filter. Look, the Kalman filter is an absolute master at estimating things. But here's the catch. It assumes the world works in a very clean, predictable way. So what happens when reality just refuses to play by those neat and tidy rules?
And right here, you can just see the conflict. The Kalman filter lives in a world of straight lines and simple bell curve randomness. But real traffic? That's just pure chaos. It's full of sudden jams, weird driver behavior, and all sorts of events that just do not fit into that perfect little box. Let's get really specific for a second. A line of cars doesn't just grow steadily, right? It can suddenly spill back and block a whole intersection. That's a totally nonlinear event. Or maybe a camera miscounts cars because of a weird shadow. That's not the kind of predictable error the filter expects. And probably most important, when we do something, like change a traffic light, we are fundamentally changing the rules of the game. The standard Kalman filter just wasn't built for that level of real-world mess.
Okay, so if the Kalman filter isn't quite up to the task on its own, what are our options? Let's meet the two core philosophies we're going to bring together to tackle this one very messy problem. So on the other side, you've got the particle filter. Now this is cool. Instead of making one single best guess, it basically unleashes an army of thousands of tiny guesses, or particles. Think of each one as its own little hypothesis. Hey, maybe there are 10 cars. Maybe there are 12. Wait, maybe there are only 9. Each of these little ideas is then weighed based on how well it actually matches what our sensors are seeing in the real world. It's this super flexible approach that's just perfect for these messy, nonlinear problems.
And it all works in this constant 4-step cycle. First, it predicts where all these little possibilities might go next. Then, it weighs them. The particles that look more like reality get a higher score. Step 3 is basically survival of the fittest. It kills off the unlikely guesses and makes copies of the really promising ones. And finally, it averages out all the survivors to give us one single, really solid estimate.
But, and this is a big but, while the particle filter is incredibly flexible, it's no silver bullet. Keeping track of all those particles can be really slow and needs a ton of computing power. And sometimes the whole swarm of guesses can just drift away from the actual truth and lose its precision.
And this, right here, brings us to our solution, the Adaptive Kalman Particle Filter, or APKF for short. This is where we truly get the best of both worlds.
This is the big idea, and it's so smart. Instead of picking one filter or the other, we just combine them. We take the super precise, efficient math of the Kalman filter, and we embed it inside every single particle in our swarm. So now, each one of those tiny hypotheses gets its own personal, high-speed fact-checker. This gives us a way smarter cycle. We still propose where each particle's going, but now we're action-aware. We actually factor in things like a traffic light turning green. Then comes the magic step. Each particle's guess gets instantly refined by its own little Kalman update. After that, we do the whole weight and resample thing, but with a final, really powerful twist. The filter adapts. It learns in real time whether it should trust its own models more or the data coming in from the sensors.
Okay, I know, an equation. Don't worry, the idea behind it is actually really simple. All it's saying is that our new, better estimate is just our original guess plus a small correction. And that correction is based on the error, the difference between what our sensor saw and what our particle predicted, multiplied by a trust factor, K. It's just a really elegant way to nudge every single guess a little bit closer to reality. Theory is great and all, but let's see how this thing actually performs when the rubber meets the road. We're going to drop the APKF right into the middle of a traffic jam.
All right, here's the scenario. Our traffic model is predicting there should be about 10 cars waiting at the light. But our sensor out on the street, which we know can be a little flaky, is only counting 8. So who do you trust? The model or the measurement?
So the first thing the filter does is calculate something called the Kalman gain, which we call K. For this example, let's just say it works out to be 0.4. You can think of this as a trust knob. The filter calculates it based on how much it trusts the model versus how much it trusts the sensor. A value of 0.4 here means we're going to lean a little more on our model's prediction, but we're still giving a lot of weight to what that sensor is telling us.
Now we just plug those numbers into that core correction formula. We start with our model's prediction of 10 cars. Then we add the correction. That's our trust factor of 0.4 multiplied by the error, which is just the sensor reading of 8 minus the prediction of 10.
And the result is 9.2 cars. Now notice, it's not 10 and it's not 8. It's an intelligent compromise. Instead of just blindly trusting one source or the other, the APKF finds the most likely truth hiding right there in the middle. This gives us a way more robust and reliable picture of what's actually going on.
So, okay, it's a really smart way to count cars. That's cool. But let's zoom out for a second because the implications of this hybrid approach are way, way bigger than just traffic.
So here are the key takeaways, the APKF superpowers, if you will. First, it's a hybrid, so it gets the precision of one filter and the flexibility of the other. Second, it's action-aware. It understands that our decisions actually change the system. And third, it's adaptive, meaning it's constantly learning who to trust. It all adds up to a system that isn't just smart, it's wise.
And this is where it gets really, really exciting. If we want to build the next generation of truly smart systems, like a traffic grid that optimizes itself using reinforcement learning, that AI needs to know what's really happening on the ground. The AKF is so crucial because it provides that reliable ground truth. It feeds the AI a clean, accurate picture of reality so the AI can make genuinely intelligent decisions.
And that really just leaves us with one final thought. We've seen how this works for traffic, right? But just imagine applying this level of adaptive, hybrid thinking to other really complex systems. We're talking finance, climate science, global logistics. What new insights could we possibly unlock if all of our models were this good at navigating messy reality?